Welcome to Texas State University's Chemistry 2342, Organic Chemistry 2. I'm Dr. David Irvin, and I'll be your guide for this system. We're looking at Chapter 13, Part 4, the DielsAlder reaction. Okay, so we learned before in the earlier part of the chapter that conjugated dienes have different reactivity. And this is a specific reaction using the conjugated diene in what we call a 4+2 cycloaddition. Meaning we have 4 pi electrons from the diene plus 2 more pi electrons from either an alkene or an alkyne that form a 6-membered ring with a double bond in it. That is the DielsAlder reaction. Okay. So the diene itself is used in the reaction to form part of the ring, and then we have the other part of it called the dienophile, or the thing looking for the diene. When it does that, it forms a new 6-membered ring, and there's at least one double bond in that ring. So if you look at the general DielsAlder reaction here, we'll see that we have our diene has a total of 4 electrons in it, and then our dienophile has 2 more electrons in it, and we have these pi electrons reaching out to form a new sigma bond here, these pi electrons reaching out to form a new sigma bond here, and these pi electrons moving over to where there's already a sigma bond, therefore generating our last bond, which is our double bond. So if we follow the atoms together, looking at it in this direction here, we always have the double bond formed on the diene portion of the reagent. And then there can be a double bond here if you're starting with a triple bond. But we formed 2 new sigma bonds at the ends of the dienophile. Okay? So the 3 curved arrows indicate that it happens all in one cyclic movement of all the pairs. We break 3 pi bonds forming 2 sigma bonds and 1 pi bond in what we call a concerted process. It happens all at the same time. And we know this is true because some of the reaction products, we always get these cycles, these 6-membered rings, okay? And so the new energy of each of the bonds is greater than the pi bond that was broken. So typically DielsAlder reactions release energy and are exothermic. In this reaction, electron-rich dienes react as the nucleophile, and the electron-poor dienophile acts as the electrophile. Okay, so what are some other ways to look at this? So in this case of the first one here, we have our just regular butadiene here, and that is our electrophile. Now we have this is our dienophile. And notice we have these 2 carbonyl groups on here. Those 2 carbonyl groups are going to withdraw electron density away from that double bond, making it more susceptible to attack by the nucleophile. Okay? So when we do that, the first step will actually add across the first double bond, but we can add another equivalent and it'll add across the second double bond. Notice that the double bond formed here is in between where the dienes were. That's where the double bond ends up on the system. But we always formed that 6-membered ring, and the double bond is in between the 2 dienes. Okay, so we can actually do it where we can make the reaction happen even faster. For example, if we put these groups here, these can act as electron donating groups, and we can add across a triple bond. In the case of adding across a triple bond, we are going to have the formation of a double bond in between our 2 dienes, which we see here, but we're also going to maintain a single. Only one of those pi bonds is used to create the new sigma bond. The other pi bond remains in that same location. So we'll see that again and again when we have these triple bonds used in these reactions. We'll end up with a cyclohexadiene from the product. Now, there's no restriction on what the diene or the dienophile can be. So if we look at this here, we have cyclohexadiene, and it's locked in that cis configuration. And then we have this right here, which is malic anhydride. And so we have 2 electron withdrawing groups on it right here, and we have our dienophile right there. And so when we do this, we end up with a fused multi-ring system. Okay, so part of the ring here is from the cyclohexadiene, and that's this one right here. Notice we have the double bond in where we've made those two new bonds. We have the other ring that forms here across the other system. And so these electrons are the ones that came from the diene. These electrons are the ones that came from the dienophile to generate those two new sigma bonds. But all the other rings stay intact. Okay, so we have some rules associated with the DielsAlder reaction. First and foremost, the diene can only react if it adopts that S-cis configuration. They have to be facing the same direction to be able to do this reaction. So in the case of, if we had this methyls 1,3-butadiene, we'd have to rotate around that sigma bond. Remember, sigma bonds do free rotate, double bonds don't. So if we can rotate around that to create our cis conformation, we can then do this reaction. Okay, so even if we had that dimethyl substitution, we could still do that rotation and get to the dimethyl S-cis configuration. Okay, you only do that rotation around a sigma bond. The pi bonds are locked into their E or Z configuration. Okay, now if you have a substrate that's locked into that S-cis, like this cyclic compounds right here, they are exceptionally reactive because you don't have to worry about rotation. You don't have to wait for it to take on that S-cis configuration, and they are much more reactive. However, if you have them locked in a system where they cannot achieve that S-cis, then they do not react as dienes in the DielsAlder reaction. Okay, the second thing we need to think about when we're talking about the DielsAlder reaction is that electron withdrawing substituents on the dienophile, the double bond or triple bond, increase its reaction rate. And if you think about it, the diene is acting as a nucleophile. So the less electron density you have on the dienophile, the more reactive it'll be toward that species. Okay, so the diene, the conjugated diene, is the nucleophile, and therefore the dienophile is the electrophile. By having groups that would draw electron density from that, it creates a more reactive species. So common dienophiles include stuff with just like an aldehyde on it or a ketone, or you can even have a carboxylic acid ester. This is an acid anhydride, and we can also use things like benzoquinone. Notice they can be rings or not ring systems, but they all have carbonyls in conjugation with the double bond. Okay, so if electron withdrawing groups on the dienophile enhance the reactivity, that means electron donating groups on the diene also enhance reactivity. The more electron density on the diene, the more it's going to react. So just by having a methyl group on this butadiene, it enhances the reaction and it happens at a lower temperature. In this case, we're going to react it with this propanol, or the vinyl aldehyde right here, and we're going to generate our new 6-membered ring with our dienophile on one side and our diene reacting on the other. Remember that this bond here was formed from the dienophile electrons, and this bond here was formed from the dienophile electrons are these, and the diene electrons are the double bond there. Okay, so a lot of the good electron donating groups tend to be alkyl groups because they have a fairly nonpolar bond, or alkoxy groups. Those oxygens act as electron donating groups. Now, you don't have to have electron withdrawing groups, but it really does increase the rate of reaction. So let's talk about the stereochemistry associated with this. Depending on what your different materials are when they react, they will retain their stereochemistry. For example, we have two derivatives of this dicarboxylic acid available to it. In its cis form, these dicarboxylic acids are called maleic acid. Okay, notice that because you don't have free rotation on that double bond, they are locked into that, the two carboxylic acids being cis to each other. In the other isomer of it, we call that fumaric acid. The two double bonds are trans to each other. I'm sorry, the two carboxylic acids are trans to each other. So that being said means that they will retain that location. So when these electrons reach out to grab here and these electrons reach out to grab here, we'll form, of course, our double bond in the middle, but the two carboxylic acids are going to be cis to each other on the same side. So both products give us cis product with the carboxylic acid being next to each other. Okay. Now, if they have the trans configuration during the dienophile, that means they are still going to be opposite each other, and we're going to get enantiomers because they're going to be on opposite sides of the ring from each other, not the same side, and therefore they're going to be retaining that trans configuration in the final product as well. Okay, so now we have what we call a preference for endo versus exo orientation. Okay, so what endo orientation means is that our electron withdrawing group is going to be closest to where our diene came in to attack it. Okay, so in cyclic dienes, we have that happen because the dienophile has to come into the top or the bottom of the configuration, and the electron withdrawing group is going to try to be closer to the electron of the pi cloud of the diene. Okay, so in this case right here, if the electron withdrawing group was closest to the alkene coming in, it is going to be in close proximity to the new double bond formed. Okay, and we call that the endo configuration. Okay, notice in this configuration here, the Z is farthest away from our double bond right here, and that's what we call our exo configuration. Okay, so in the endo, the substituent is oriented cis to the longest, most, or more unsaturated bridge. The exo is oriented trans to the longest or more unsaturated bridge. Let's take a look at that again and see why it does that. Okay, so as our compound is coming in to get to our transition state so we can do our cycloaddition, remember it's concerted, it happens all at once, so we have to have them in close proximity before they do it. We will see that as it comes in and aligns, we'll want to get it to, if it comes in to this top right here, it's going to give us our product with our electron withdrawing group closest to our double bond here. And that's the endo configuration here. Okay. In this case right here, we'll also have it such that the two electron withdrawing groups are endo, closest to where the diene was. And this is also the endo configuration. Okay. So why does it prefer the endo configuration? Okay, so in the transition state, as the dienophile moves in close, right, we have the electrons of the diene up here are going to start interacting with the electron withdrawing group of the dienophile. So the electrons in the electron poor section here is going to be attracted to the electron rich section of the dienophile. Therefore, the electron poor section is going to be closest to those electrons, trying to, bond through space. When it does that, it gives us our new transition state here as those bonds are forming. Because that electron withdrawing group is close to there, it gives us our endo product. So what would it look like if it was the other way around? If our electron positive, partially electropositive section here was not attracted to this side, to these electrons on the diene, then they would be on the outside here. And so when we formed our new transition state here, our electron withdrawing group would be away from it and giving us our exo product. Okay. So it has everything to do with the idea that that partially positive, that electron withdrawing group is going to pre-associate with that electron cloud. When it pre-associates with that electron cloud, it sets the stage for it bonding in its concerted fashion all at once, giving us our endo as our major product. Okay, so when we have unsymmetrical reagents, we still have specificity on here. Okay, when both the diene and the dienophile are unsymmetrical, we can form two possible products, but we can figure out which one is major based on its electron contributing resonance structures. Okay, so in this case right here, we have the diene and it has a methoxy group on it. And the methoxy group is the electron donating portion of that system, right? Because it's helping add electrons to the system. In the case of our dienophile, it is the propionyl. So it has the electron withdrawing group is the carbonyl group there. And so what we'll see is that from our resonance structure contributions here, this is going to be our partially negative side, and this is going to be our partially positive side because of the resonance structure. And in our resonance structure, this is going to be our partially positive side, and this is going to be our partially negative side. So our partially negative side is going to be attracted to our partially positive side. And on the other side of the compound, our partially negative and partially positive will also be attracted. That's going to set the stage for them to drift in and become a preferred position for them to form their two new bonds. And therefore, we're going to end up with one compound being preferred over the other. And in this case, we have it where the electron donating group and the electron withdrawing group are in closest proximity to each other. So if we look at this isomer here, we have our electron donating group from our diene and our dienophile in close proximity to each other. Here, they're in the opposite proximity to each other, and therefore closest proximity is going to be the preferred reaction. Okay, so that is a sum up of the DielsAlder reaction and how it relates to conjugated dienes.